This is the M1A2 Abrams, the U.S. Army's main battle tank, and one of the most advanced armored vehicles in the world. It's armed with a cannon over 5 meters long that can punch through nearly a meter of rolled homogeneous steel armor from 2 kilometers away. That's the equivalent of punching through a car from end to end, from 2 miles out. Depleted uranium plates protect its turret and hull. Not just any uranium, this is a byproduct of nuclear enrichment, 1.7 times denser than lead. When a sabot round hits these plates, the uranium doesn't just stop it. It actively disrupts the penetrator through adiabatic shear banding. In layman's terms, the armor fights back. The latest upgrades added an additional anti-mine underplate, reactive armor tiles over the flanks that explode outward to disrupt shaped charges, and a trophy active protection system on top Israeli-designed radar that detects incoming missiles and literally shoots them out of the air with shotgun-like blast projectiles. But these additions raise the Abrams' fully loaded combat weight to 78 tons. That's as much as a Boeing 737-800 on takeoff, or 20 Ford F-450 pickup trucks stacked on top of each other. 20. Yet here it is, racing down dirt roads at highway speeds, jumping and firing midair, wading through meter-deep mud, drifting it like it's a Toyota AE86 through corners that shouldn't accommodate something twice the width of a car. And it's possible thanks to its powertrain. Its powertrain is a jet engine attached to a gearbox taken from a helicopter. Specifically, the AGT-1500, a 1,500 horsepower gas turbine derived from the Lycoming T-55 turboshaft engine that powers Chinook helicopters. It can generate full power out of any flammable liquid diesel, gasoline, jet fuel, kerosene, even vegetable oil in a pinch. The multi-fuel capability was a Cold War requirement. If logistics broke down, Abrams crews could siphon whatever they found. But the real magic is the torque curve. A diesel engine builds power gradually as RPMs climb. A turbine hits maximum torque almost instantly. In the time it takes a diesel-powered tank to spool up from idle, a turbine-powered Abrams is already moving behind cover. That split second can mean the difference between eating a missile and eating breakfast. No other tank today, bar one, uses something like this. The exception is the Russian T-80, which also uses a turbine, but even Russia abandoned the design after the Soviet collapse. But the amount of fuel it consumes is the Abrams' biggest handicap. In Ukraine, this turns into a logistical nightmare. An Abrams consumes a liter of fuel to travel just 142 meters. A German Leopard 2 manages twice that distance on the same liter. An Abrams can be fully fueled in the morning and running on fumes by evening just by idling in place, because turbines drink fuel even when standing still doing nothing. It can't travel as far or sortie as often as other tanks because of a turbine it wasn't even supposed to have and that the U.S. Army is going to ditch this year. Out of 31 M1A2 Abrams tanks delivered to Ukraine, 27 have been confirmed lost. That's an 87% loss rate. How did the Abrams end up like this? And why did it fail in a war it was supposedly built to fight? To explain this, we have to follow the incredible evolution of tank engines going back 100 years. Number, the birth of armored power. Designing a tank engine is an exercise in managing contradictions. Tanks want to install as much armor and firepower as possible, which comes with the cost of a lot of weight. To move all that, the engine needs a lot of torque, specifically low-end torque. Torque that's available at low engine RPMs, when the tank is just beginning to move and has the most inertia to overcome. The easiest way to do that is to increase engine displacement. Larger piston cylinders hold bigger explosions, raising the twisting force at the crankshaft. But an engine like this takes up more space within a tank hull, which means a bigger hull with more area to cover with heavy armor, which then needs a bigger engine to move around. We're back at square one. There were no specialized tank engines to solve that problem in World War I, when tanks first saw combat. These were secretive emergency projects designed with whatever was available. The British Mark. I trapped 8 men in a closed steel box with a carbon monoxide fuming Daimler Knight, one 6-liter sleeve valve engine that barely managed 105 horsepower while rattling their ears off or burning them with exposed red-hot exhaust pipes, top speed. 6 kilometers per hour. That's a walking pace. The French Saint-Chamond was even worse. A 2-3-ton monster powered by a Panhard 4-cylinder engine that couldn't handle the weight, leaving it constantly broken down and vulnerable. These were not weapons of maneuver. They were mobile bunkers designed to crush barbed wire and cross trenches. Engine technology hadn't caught up with ambition. World War II, the Great Acceleration. Tank evolution really began to accelerate in World War II. Early engagements between Allied and Axis forces quickly revealed that the U.S. Army's 1.8-ton M2 medium tank was beyond obsolete. It didn't have the armor to stand up to German 75mm guns, nor the weapons to defeat panzers from any range. So engineers rushed to create a tank with heavier armor and its own 75mm gun. The result was the slapdash M3 Lee, with its main gun jammed into a sponson on the hull side, later perfected into the war-winning M4 Sherman. The Sherman was around 30 to 33 tons, depending on the variant. Why not more? Like the British-designed Churchill at 40 tons. The U.S. Army had been trialing heavy tanks of their own, but they could never fit into the Allied logistics chain. American forces needed to cross oceans before they could fight on the battlefields of Europe, Africa, or Asia. That meant any tanks they brought with them had to be easily shipped and deployed by the equipment at hand. The Liberty ship, backbone of Allied logistics, used cargo hoists that usually couldn't handle more than 30 tons. The landing craft which brought tanks ashore, like the LCM-3 during D-Day, could only carry a single 30-ton load. Prefabricated Bailey bridges for crossing rivers in enemy territory also imposed their own size and weight restrictions. It made no sense to build a supertank that would never reach the battlefield. The choice of engine for the M4 Sherman was similarly practical. It started with the 340 horsepower Wright Continental R 975, a lightweight 9-cylinder radial engine that was robust, reliable, and most importantly, already in mass production for aircraft. Later versions bundled together whatever engines were available just to keep up with demand from the front line. But other variants experimented with engine arrangements looking for the perfect formula, like the M1A2 which came with 5 Chrysler inline 6-cylinder engines all driving their power to a single drive shaft, combining to create a 370 horsepower, 25-liter displacement, 30-cylinder multibank contraption called the A57 Multibank. Chrysler even claimed in a 1944 issue of Popular Science that the tank could keep moving with 2 of its 5 engines knocked out. The Germans didn't have such strict logistical restrictions on their tanks. Their tanks could ride trains with multi-axle flat cars and then just drive the rest of the way to the front under their own power. The German rail network had a higher loading gauge than anything in the UK or US, allowing for wider, taller, heavier vehicles. The result was a number of designs with superior guns and armor 2 to 3 times thicker than any Allied vehicle. The infamous Tiger I. I was a 5.4-ton box with 10 centimeters of face-hardened steel over the front, impervious to the Sherman's 75mm gun from any angle at any range. When the Allies brought in bigger guns to deal with the Tiger I, the British one, 7-pounder, the American 76mm, the Germans developed its successor, the 6.8-ton Tiger II, with 15 centimeters of sloped armor, which made the effective armor thickness 23 centimeters when angled. In the last year of the war, the 7.2-ton Jag Tiger appeared, with 25 centimeters of armor and a massive 128mm gun that could knock out Shermans from over 3 kilometers away. To deal with the ever-increasing weight, the Germans simply used the same Maybach 512 liquid-cooled engine and scaled up its displacement. The first Tigers to roll off the manufacturing line came with an inadequate 2.1-liter engine, the HL210. To upgrade it, they simply increased its cylinder bore by 5mm to create a 2.3-liter displacement engine, the HL230. At 700 horsepower, it was still not enough. One of the best engines of the war, stretched to its limit by ever-increasing weight. It gave the Tiger a power-to-weight ratio of around 12 to 13 horsepower per ton. Then they threw it into the 7.2. Mechanical unreliability killed more German tanks than Allied shells did in the last year of the war. Number. The Soviet school of thought. Throughout the war, the Soviets took the brunt of Axis aggression. and they learned hard lessons on how important it was to balance offense, defense, and mobility. They used these lessons to design the T-44. Their genius idea was to take the engine of the T-34 tank, the V-2, the most prolific military V-12 diesel in history with over 100,000 units produced, and simply turn it 90 degrees, mounting it transversely, and package it with its transmission in a compact bay in the rear. This lowered the height of the hull by around 30 centimeters, not just making it a smaller target, but allowing critical weight to be shifted to front armor where it was needed most, while creating room for a wide turret that could hold a high-caliber gun. The T-44 granted the firepower and protection of a tank twice its weight through clever packaging. While it didn't get a notable service record and was soon replaced by the T-54-55 series, we can trace the compact design and hull layout of all Russian tanks today, from the T-55 to the T-90 directly back to the T-44. Number. The Cold War stagnation and revolution. What followed was a period of relative stagnation. The Cold War meant that tank development continued, but without technological breakthroughs. The improvements were just incremental. Engines got slightly more powerful. Armor got slightly thicker. Guns got slightly bigger. But the fundamental design philosophy hadn't changed since 1945. In the mid-1960s, however, tank design philosophy shifted radically. Finding targets and devising a firing solution had been considerably sped up by the introduction of advanced optics, laser rangefinders, and fully stabilized gun barrels. High-explosive anti-tank ammunition and armor-piercing fin-stabilized discarding sabot rounds had been developed into high-velocity projectiles that could penetrate up to half a meter of steel. No tank could carry enough armor to protect itself reliably against these new threats. Combined, these features meant that tank combat devolved into a brawl, where the first one to find and shoot their opponent almost always got the kill, and the only way to survive was to rapidly duck behind cover after firing, shoot, and scoot. The implication for tank design was that most armor could be discarded in favor of maximum maneuverability, which raised the importance of engine design even higher. West Germany met this design challenge with the Leopard 1-inch 1965. It used a 1.0-cylinder supercharged 3.7-liter MTU MB 838 diesel engine producing 830 horsepower. It carried minimal armor, only about 70 millimeters at its thickest, and a stabilized 105 millimeters Royal Ordnance L7 gun. The Leopard 1 weighed in at 40 tons despite its hull being over 8 meters long. It was designed to fight outnumbered and win through superior mobility. Soviet tank design took another direction with their T-64A, which entered service in 1967. They raised the stakes with a massive 125 millimeters caliber cannon, the first smoothbore tank gun in service, and developed an autoloader system to handle ammunition that exceeded 20 kilograms per round, eliminating the need for a human loader and allowing the turret to be smaller. New composite armor called Combination K placed glass-reinforced plastic between traditional steel plates, offering better protection than the same full thickness of steel at much lower weight. They packaged it with an innovative power plant design, the 5TDF, a two-stroke, opposed, piston, 5-cylinder engine with 10 pistons total, 2 pistons in each cylinder, pushing toward each other, meeting at the center. This design eliminated heavy cylinder heads and valves entirely, resulting in an engine with twice the power density of the American M60's Continental AVDS 1790 diesel. The 3.8-ton T-64A entered service in 1967 as the most advanced main battle tank in the world, but that came with a cost. The 5TDF had to be driven perfectly to avoid damage. The complex gear train keeping everything running smoothly had its work cut out for it in a tank battling it out on rugged terrain. Heat concentrated in the center of the two pistons, with no cylinder head to absorb it. Without adequate cooling, the pistons could absorb enough heat to expand and seize within the cylinder. Engine life was measured in hundreds of hours, not thousands. The T-64A was reserved for elite fighting units stationed in East Germany. Regular units got the simpler T-72. The most innovative high-power density engine isn't always the best choice. Reliability matters. Number. America's Crossroads. The MBT 70 disaster. Watching these developments, the U.S. Army found itself at a crossroads. It could continue with incremental improvements of the M60 based on a hull with World War II heritage dating back to the Patton series, or take a great leap forward to address present and future Soviet threats. It chose the latter path by investing in a joint venture with West Germany in what would become the disastrous MBT 70 program. On paper, the idea was great. Two NATO allies, the US and West Germany, would combine their expertise and share the costs of developing a revolutionary tank that would glide over the battlefield at 70 kilometers per hour on high-drop pneumatic suspension, outranging anything the Soviets had with a 152 millimeters auto-loaded gun that fired Shilolog missiles, all while staying under 45 tons. In practice, it was a disaster. Neither side agreed on anything from the choice of major components like the gun or engine, or even whether to use metric or imperial units. The Germans wanted a diesel engine. The Americans insisted on a turbine. The Germans wanted a 120 millimeters smoothbore. The Americans wanted their 150 2 millimeters gun launcher. The driver's position was in the turret on a rotating platform, innovative but terrifying for the crew. The U.S. Army's attempt to salvage it, later rebranded as the XM-803, also failed after Congress cut funding, citing excessive cost and complexity. After 7 years of effort and $11 billion in today's money spent, no new tank was ready. Number. The turbine gamble. But not all of it went to waste. The U.S. restarted its search with a stricter budget and looser requirements. Chrysler and General Motors both made proposals that used a conventional 105 millimeters gun and incorporated the latest NATO composite armor schemes derived from British Chobham armor research. Their main distinction was in the choice of engine. General Motors proposed a diesel, a tried-and-true AVCR 1360, an air-cooled V12 producing 1,500 horsepower. Reliable, fuel-efficient, and based on decades of experience. The Chrysler proposal was what was to become the M1A Abrams, fitted with the AGT 1500 turbine on traditional torsion bar suspension. Chrysler knew this was a risky move. Jet engines and tanks had an uncertain reliability record. The Soviet T-80 wasn't even in service yet, so there was no precedent to learn from. And turbines had an extreme thirst for fuel, even when idling. But they did offer notable advantages. They could burn a wider selection of fuels critical if logistics broke down. They took up less space than a diesel engine. The AGT 1500 was compact enough to allow the Abrams' distinctive rear hull slope. Most importantly, they could reach maximum torque output nearly instantly. If we look at the torque versus RPM curves of a turbine engine compared to a diesel engine, we see a massive gap all the way up to 2,100 revolutions per minute, 70% of the maximum output shaft speed. In the time it takes a diesel-powered tank to spin up its heavy rotating assembly, a turbine-powered one would already be moving behind cover. That acceleration advantage could mean survival. In the end, the Chrysler design won the contract. Tactical mobility in the Cold War era was deemed a sufficiently good argument, and the higher fuel consumption wouldn't matter in the lightning-quick battles NATO expected to have with the Soviet Union, battles that would be over in days, maybe hours, before logistics became an issue. Others claim Chrysler was chosen to save it from bankruptcy. The company was in financial trouble, and the tank contract was a lifeline. And so, development of the Abrams began in 1976, the first new main battle tank in America's arsenal in 2 decades. Number. The first jet tank battle. The Abrams had the best survivability and cross-country performance of any tank of its time, something it actually demonstrated in trials against the Leopard 2. Where it fell short in fire control, the German tank had better optics initially. It made up for it, with better crew experience. More comfortable, quieter, easier to operate. The turbine was smoother than any diesel, reducing crew fatigue on long movements. But that lead did not last for long. The Soviets entered their own turbine-powered tank into service in 1976 too, the same year as the Abrams. The T-80 used a purpose-built GTD 1000 turboshaft, producing 1,000 horsepower, and used that excess power to move around a heavier 4 2-ton tank with enough composite armor to withstand Western 105mm guns. The Soviets valued the turbine's ability to start up in Arctic temperatures of -40 degrees Celsius, without preheating, a critical advantage in a northern European winter, and keep running for longer between maintenance intervals. The T-64's complicated opposed piston 5 TDF struggled with both these issues. Soon after, the T-80B upgrade rolled out in 1980 to face the M1 Abrams directly. It had 1,100 horsepower, even thicker armor, and the ability to fire 9K 112 Cobra missiles from its 125mm barrel on the move, with a 4-kilometer range. A tank that could engage helicopters and tanks beyond the range of any NATO gun. 2 years later, reactive armor started being added to Soviet tanks to deal with NATO's shaped charge missiles and infantry anti-tank weapons. Shaped charges work by focusing explosive energy into a hypervelocity jet of molten metal that cuts through armor like a blowtorch through butter. Reactive armor disrupts that jet by detonating outward, scattering the jet and absorbing its energy. By the early 1980s, the Soviet tank fleet was being upgraded with Contact, one explosive reactive armor bricks. The T-80B with Contact, one was arguably the most lethal tank in the world. The U.S. Army responded with a comprehensive upgrade package, the M1A1. It got additional armor, including depleted uranium plates so dense they can break up sabot round darts through sheer mass, better fire control electronics, and crucially, the Rheinmetall 120mm smoothbore gun the Germans wanted to give it since the failed MBT-70 joint venture back in the 70s. The M1A1 would go on to dominate in the Gulf War. In the 1991 Battle of 73 Easting, American Abrams tanks destroyed Iraqi T-72s at ranges where the Iraqi guns couldn't even return fire. The turbine's acceleration let American crews shoot, move, and reposition before Iraqi gunners could acquire them. It was a massacre. But that war wasn't the war the Abrams was built for. Number. The Russian retreat from turbines. After the Soviet Union collapsed, the Russians kept designing better tanks, but they learned hard lessons from the T-80's service record. The turbine was much less reliable than expected in field conditions. Soviet logistics, never great, couldn't handle the fuel consumption. In the 1994 Chechen War, T-80s entered Grozny with full tanks and were abandoned in the streets hours later, out of fuel and out of luck. The turbine engine was also 10 times as expensive as an equivalent diesel engine, a critical factor in Russia's cash-strapped 1990s economy. The T-90, Russia's main export tank of the post-Soviet era, uses a simple, reliable V92 diesel. Since then, from Sweden to China, all main battle tanks put into service have good old, reliable, fuel-efficient, easy-to-maintain turbo-diesel engines, with one exception. Number, the American exception. The U.S. kept its jet tank. The M1A2 upgrade came in 1995, followed by a system enhancement package every few years to keep it competitive. Each upgrade added more armor, more electronics, more weight. The SEP-V2 added second-generation thermal sights and better displays. SEP-V3 added even more armor, an auxiliary power unit so the tank didn't have to idle its turbine to run electronics, and improved suspension to handle the weight. Each upgrade came with a hefty increase in weight and worsened fuel consumption. The M1A2 SEP-V3 weighs 78 tons combat loaded. That's 10 tons heavier than the original M1 from 1,980. Unlike the rest of the world, the U.S. military has an $850 billion and rising budget. It can afford to keep gas-guzzling tanks full. It has a fleet of C-5 Galaxy cargo planes to haul them across continents, an entire air force in another country, dedicated just to logistics. The problem is that all this effort might be unnecessary. Number. The Ukrainian Crucible. The M1 Abrams was designed for a world that's long gone, dashing between firing positions to fend off a deluge of Soviet tanks pouring into Europe for a few days before the bombs fell. Extreme mobility being the only way to survive tank combat was only true for a few years in the late Cold War. As the latest Leopard 2A7 or the British Challenger 2 demonstrate, modern, sophisticated composite armor layers of rubber, ceramic, and metal can absorb hits that would penetrate over a meter of steel, a far cry from the 23 centimeters of the terrifying Tiger II. Armor is back in fashion. The deployment history of the Abrams until recently involved crossing the deserts of Iraq and idling for months in Afghanistan. In these conditions, a jet engine in a tank is a disadvantage. An Abrams consumes fuel at idle almost as fast as at full throttle because the turbine never stops spinning. Crews in Iraq would refuel multiple times a day just sitting on checkpoint duty. The Abrams is finally facing Russian tanks in Ukraine, but instead of epic battles between rolling columns of armor, Ukraine is preserving its equipment. It has used the fuel-hungry Abrams in short skirmishes with hit-and-run tactics. Drive in, fire a few rounds, drive out before Russian artillery can respond. The Abrams does this well. The turbine acceleration helps, but it's not how the tank was meant to fight, and the losses are remarkable. Out of 31 tanks delivered, 27 have been confirmed lost, except for a single case of a direct hit from a Russian T-72B3 in a tank-on-tank engagement. Every other loss has been from drone attacks, anti-tank missiles, artillery, and anti-tank mines. The Abrams simply isn't fit for the modern battlefield. First-person view drones, racing drones rigged with RPG warheads loiter over Ukrainian positions waiting for an Abrams to move. When it does, they dive. The Abrams' top armor, never designed to withstand aerial attack, is thin enough for a shaped charge to penetrate. Even if the warhead doesn't kill the tank, it can destroy optics, track, or engine, leaving the $10 million vehicle immobilized for artillery to finish. Additional armor can solve some of those problems. The U.S. Army is rushing to buy top attack protection for its Abrams, sometimes referred to as cope cages, by crews who see them as desperate measures. New additions provide thickened belly armor against mines and active protection systems to shoot down incoming missiles. But these come at the cost of even more weight, beyond the 78 tons it already rolls around with. The future T-14, Armata, and beyond. The Russian T-14 Armata offers a glimpse at the solution to all this. A remotely controlled gun sits in an unmanned turret, while the crew is moved entirely to an armored capsule in the hull. This drastically reduces the volume that has to be armored, cutting down overall size and weight. The crew capsule is a survival cell. If the turret is hit, the crew lives. Powering it is a new 34.5-liter displacement 12N360 diesel engine, producing 1,500 horsepower from 12 cylinders, arranged in an X shape, an arrangement that allows it to be a lot more compact than the V12 diesels going back to the T-34. In an emergency, the boost pressure can be raised to deliver 2,000 horsepower, at the cost of some damage to the engine. While this tank may never be produced in threatening numbers, Russia has struggled to fund mass production or even complete its full development. It is an important marker for where future tank design is going. Number. The Abrams' last dance. Prototypes and proposals for replacing the Abrams have appeared over the years. The Future Combat Systems program promised unmanned turrets with enormous 140mm guns and space-age composite materials. What they shared was Cummins diesel engines producing just as much horsepower as the turbine while taking up 50% less space. The U.S. Army seems to have finally shifted course. With hard lessons learned from the Ukraine war, they have developed the M1A2 Abrams. With the latest armor technology, it aims to reduce weight to 60 tons, a 23% reduction from the current model. Powering it will be the Cummins ACE Advanced Combat Engine, an opposed piston turbo diesel paired with an electric motor. This is a hybrid tank, the tank version of a Toyota Prius. It could cut fuel consumption in half. It could give the tank the ability to sneak around in all-electric stealth mode silent, no heat signature, or lie in wait with the diesel engine turned off, hidden from infrared sensors. The electric motors also provide instant torque, negating the turbine's main advantage. The hybrid can accelerate just as fast without drinking fuel at idle. Soon, we will see if this will really be the next step in tank warfare. The Abrams was a product of its time, a Cold War warrior built for a war that never came. In Ukraine, it's facing a different kind of war, and it's struggling. The turbine that made it revolutionary is now its biggest liability. The U.S. Army knows this. The M1A2 is the admission. The age of the jet tank is ending. The question isn't whether the Abrams can survive on the modern battlefield. It's whether any heavy tank can. And as drones get cheaper and anti-tank weapons get smarter, that question becomes more urgent every day. For now, the Abrams will keep fighting, but its glory days are behind it, and the tanks of the future will look nothing like it. This was the story of the M1 Abrams, a jet-powered legend struggling to find its place in a world that left it behind. If you want to understand where warfare is heading next, you need to understand where it came from. And the Abrams, for all its flaws, is a crucial part of that story. Thanks for watching. If you enjoyed this deep dive into the Abrams, don't forget to like, subscribe, and hit the bell for more stories about the machines that shape our world.